All right, so the next part of this chapter is centripetal force. If you remember from last year, centripetal means center seeking, which always points to the center of curvature. Okay, so in circular motion, if the object is at this location, we have a force that's going to cause it to move in that circular path. And since Newton's second law says that the acceleration will be in the direction of the unbalanced force, that also works for centripetal acceleration. So if the force is towards the center, then the acceleration will also be towards the center, just from Newton's second law. And the velocity is always tangent to the curve of the circular path. We have our previous acceleration equations for centripetal motion. So we have that the centripetal acceleration is equal to v squared over r, and that the velocity is equal to 2 pi r over t squared. And when we went over just circular motion, by combining those two equations, we got this equation as 4 pi squared r over t squared. So we're going to have to use these ones specifically because we're going to have the force equals m times a. This is not used very often, especially since we should know this equation. So let's look at some specific examples here. So let's look at a car going around a turn. So if we have a curve, and there's our car, some wheels. All right, the path that the car wants to take is going to be around that curve. What is going to be keeping that car moving in a circle? So again, the force has to be pointing towards the center of curvature, and the direction of the acceleration also has to be in that direction. Well, we might not instantly think about what force is going to cause it. However, if this was in the middle of winter and there was a patch of ice here, what is the car going to do? Well, that car is going to travel in a straight line path tangent to the curve. Because what happens when you hit a patch of ice? You lose friction. So friction is the force that causes this car to make the turn. So really, with circular motion, it's still the same process for linear motion. Draw the free body diagram, write out second law, write the left side of your equation from your free body diagram. Now, with this type of problem, specifically a car going around a turn, most of the time we are looking for the relationship between the speed and the coefficient of friction and the radius. Okay, so a very standard solution here is what is the speed needed, or maximum speed that we can reach while going around a curve. So if the frictional force is what's causing the car to stay in that circular path, let's think about it as the car is on top of a surface in this perspective. So instead of looking from over top, let's look at it from behind. So as the car is making this turn, if we were following behind the car, we would always see this. Again, this is the tires, here's the bumper, there's the license plate there. All right, so we would always be seeing that part of the car. Well, in this problem, the car is trying to turn to the right so that the friction on the car is always going to be pointing to the right. The normal force is up and mg is down. So this really just looks like a simple block on a flat surface problem, so that the normal force is equal to mg, and the frictional force is the only thing causing the acceleration. So what we can do is substitute in for the frictional force mu times the normal force, which would then be mg, and that is going to cause that mass to accelerate. If we want to link the velocity to it, we would substitute in for AC our v squared over our equation. Now you should be familiar with this from last year. The mass cancels out, so it doesn't matter if it's a car, a truck, or a motorcycle going around this curve. It only depends on how sharp the curve is and the coefficient of friction. So if we manipulate this, multiply both sides by r, so I'm going to v squared is equal to multiply r over times mu times g, and again that's v squared, so I have to square root both sides. You get the square root of rug. Alright, but it goes from the process of free body diagram, Newton's second law, write the left side, substitute in the right side, solve for whatever it is you're looking for. And you can see here that the speed is directly proportional. So if it was figuring out the maximum speed on the road versus maybe some icy snow that wasn't completely slick and sliding off, what would change there is the mu. So basically, as the coefficient of friction increases, the speed that you can go around the curve increases. You can also look at it in terms of r. If we make a more gradual curve, so it's not a very sharp curve, we can go faster around that curve than we can the smaller curve. So that's a very common type of horizontal centripetal force problem, and it's one of the more complicated ones, and it's usually friction is the force that makes it more complicated. If it's an object on a string, it would just be a tension force pulling towards the center, and there would be no other substitution type situations that you would do. It would just be that force. So when it's friction, it's the only one in the horizontal direction that can give you a more complicated substitution for that problem. All right, now vertical circles get to be a little bit more complicated because gravity is always in play here. So if we have just an object on a string, so if we just had a ball and we're swinging it around so it's completely vertical, we would examine that at two separate points. All right, so if it is at this location, of course the force is always along the string if it's a tension, and the acceleration will be in that same direction. That's Newton's second law. And then the velocity would be tangent to that circle. So we're just going to do a general case here. When it's on the bottom, the tension force will be up towards the center. The acceleration would also have to be towards the center, Newton's second law. And then, again, the velocity going this way. However, there's more than one force acting on a vertical circle. We also have gravity. All right, so in each situation, gravity is pulling that object down. It is not only one force. So we would have to figure out the equations for the top and the bottom, and we should see that they're different. So if we sum up all the centripetal forces, it's going to cause that mass to accelerate, and And we have how many forces? We have 2 forces down, and like coupled motion, sometimes picking a direction to be positive makes the problem a lot easier. So we will always point or pick positive means towards center. So anytime the force is pointing towards the center, it will be positive. So in a situation like this, we're going to add the tension plus the weight to cause that mass to accelerate. But over here, if we make the tension positive, then the weight would be negative, and that would cause the mass to accelerate. Now, it's good to make towards the center positive because we want our direction of our acceleration to be positive. So if our acceleration's towards the center, we want that to be positive. All right? Because the tension force has to be greater than the gravitational force, or else the object would not go up in that circle. It would not be going this way. It would end up curving down. All right, and we can see that from this equation here, that the tension has to be greater. If we manipulate that over, the tension will equal mg plus ma, okay, which is this much greater than the weight. And then over here, the tension would be this much less than the weight. All right, now we're going to look at some more specific examples for vertical circles in the next video.